Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The 19th century French mathematician Sophie Germain once remarked that algebra is but written geometry and geometry is but drawn algebra. So what did she mean by this? She meant that in many ways, the study of algebra and geometry are equivalent. So in this video, I want to show in what sense that is that true. And the notion that I want to introduce, which codifies that, is the notion of duality. Okay, so let's begin by some motivation. And when we talk about geometry here, you can talk about geometry in lots of contexts, not just the context of algebraic geometry. So I'll start with the one which is the easiest to understand, which is topological spaces. But it's quite easy to see that it also applies if our geometric objects x and y are instead smooth manifolds. So one of the points of looking at geometry algebraically is to introduce functions on these geometric objects. So if the geometric objects are topological spaces, we can look at continuous functions on x, which are r-valued. If we're thinking of x as a smooth manifold, we can look at smooth r-valued functions on x instead. Okay, so suppose we now have a morphism of these geometric objects, x to y. So either continuous map of topological spaces or smooth map of smooth manifolds. We have to involve also some function on, let's say, y first. So f is a function of y, so either continuous or smooth, as the case may be. And the point is, from this diagram, it's clear that once you're given this function, you get for free a function from x to here, which is also continuous if these two are continuous, or smooth if these two are smooth. And that's just by composition. So we call this composite phi upper star of f. So it's just you do phi first, and then you do f. So what you see here is that, let's suppose we fix this phi here. That means as you vary these f's across the functions on y, these real valued functions on y, which are respect the geometric structure, you'll get various functions on x. So you have this phi upper star is now a function itself with domain functions on y mapping to functions on x. So note that the morphism on the geometric objects goes from x to y, but this is called the pullback, and it's called pullback in the sense that the functions on here get pulled back to functions on here. So it goes in the opposite direction to the original map on geometric objects. And that's one of the reasons why this phenomenon here is referred to as duality. Because when you take, for example, the dual of vector spaces, it sends maps to maps in the opposite direction. Okay, so that's what happens in a very simple geometric examples of topological spaces and smooth manifolds. And let's see how that plays when we look in the context of algebraic geometry. Okay, so there's the algebraic version, and we'll look at affine varieties. So we'll fix an algebraically closed field f. And there are various versions of looking at this subject, and I'll start by looking at the extrinsic definition. And I'll explain what this extrinsic means in a little while. So let's start with the simplest cases. So the first varieties you look at in algebraic geometry are the affine spaces. So what's a map from affine M space to affine N space? When is it regular or algebraic? Okay, so this is the analog of the idea of continuous or smooth in the context of topological spaces, respectively smooth manifolds. So if we're looking at affine varieties, we want to look at regular or algebraic morphisms. So let's input some M tuple inside here. And of course, you can write down the output in terms of its coordinate functions, phi 1 up to phi n. And the basic idea is that these coordinate functions are just functions on this AM. And what type of functions are they? They're just polynomial functions in the variables x1 up to xn. So essentially, they're just elements of the coordinate ring of AM. And what about general varieties, morphisms of general varieties, x and y? Well, being a variety means that x is some subset, a closed subset of some AM, and y is some closed subset of some an. So by appropriate restriction of something like that, you can get morphisms of varieties. So this is what we mean by looking at geometry extrinsically. Here we have x and y, but to make definitions, we have to see that x and y are sitting inside something else, some ambient affine space. And hence this is an extrinsic definition. So we've defined what it means to be an algebraic or regular morphism of varieties. And the point is, well, do we have a similar algebraic phenomenon here? And the answer is yes. In this case, you can look at the coordinate ring of y, and there's an induced F-linear ring homomorphism from f of y to f of x. And it's basically just this principle here at work. And to see why it's a ring homomorphism and how it works, it's best to look at a little example. Okay, so let's see a simple example of an algebraic morphism between varieties. So suppose we have phi from A1 to A2, and it's defined very simply by sending the point z inside this affine line to the two tuple z plus 1 z squared. Now this is an algebraic morphism because the two coordinate functions here are polynomials in z. So certainly that's what we have. And the other thing we can look at is to see what's the corresponding map that you get on the coordinate rings. So that's going to be a map which is a pullback, which pulls back functions on here to functions on here. So it goes from FA2 to FA1. Remember this you can identify with polynomials in the two variables x and y, and this with polynomials in the one variable z. Okay, so let's see what happens. So let's pick a function here. The functions that you need to give are x and y. So once we know where x and y go, since this is an F-linear ring homomorphism, you'll have determined the whole ring homomorphism. Let's look at the function x. How do we get the corresponding function of z here? Well, what you do is you start with a point here, say z. You apply this one, which sends it to this point here, maybe a point like this here. And then you have to take the x function of this point, which is just to pull out the x value, z plus 1. Z plus 1. Similarly, if you want to see where y goes, y is a function from here to f, which just picks out the y coordinate. So if you compose it with this map phi here, z gets into here, and then when you pick out the y coordinate, you get z squared. And that's how you determine this map on coordinate rings. It's fairly simple. And the other thing that you see about it is that once you know what this ring homomorphism is, you can very easily recover the original map. Because the x goes to z plus 1, that tells you what this function is, and the y goes to z squared, that gives you this coordinate function here. So actually these two descriptions are equivalent pieces of information. So that's rather nice thing, is that this ring homomorphism captures all the information about this morphism here. Okay, so let's do some remarks. Remember, in our definition of a morphism of varieties, we had an extrinsic definition, which says that you get morphisms of varieties by restricting this. So let's see an example of how that works. Well, let's look at the image of this map. Well, if you had z squared, we know that that's simply the graph of some parabola with vertex at 0 here. But since we shifted the x values by 1, we shifted by 1 across like that. So that's going to be the image when we draw, at least in the case of the real numbers, the way we think of it is this parabola here. And one can check quite easily that the image of phi is indeed that subset of A2 of all points which satisfies this polynomial equation y equals x minus 1 all squared. So what does that mean? That means when you map this A1z to this A2, it maps to its image, this curve C here, and then you can just include this C into A2. So this also gives you a map from A1 to this variety here, C. Just by restricting. We just restrict the codomain to, well, it certainly lands inside this subset, so we can restrict to this C here. Let's see how this plays when you look at the coordinate rings, because this is reflected completely in what happens there. Okay, so let's look at this ring homomorphism and look at the kernel of this. Okay, so let's look, for example, at this expression here, y minus the square of x minus 1 squared. Well, when you apply phi star to y, you get z squared. When you apply phi star to x minus 1 squared, you'll get z squared as well. So phi star of this difference is also 0. And since the kernel of phi star is an ideal, you certainly get this whole ideal in there. And if you play around with it a little bit more, you'll actually see that this ideal is the whole kernel. Okay, so what does that mean? It means that actually, since you have a kernel of this map, you can factor this map to this modulo the kernel. Okay, so that's fxy modulo fxy quotient out by this ideal here. And then this first isomorphism theorem tells you that this, in turn, maps to this f of z. So the factoring of this ring homomorphism completely reflects the factoring of the morphism of varieties here. Okay, so let's now look at the intrinsic definition of the morphism of varieties. And let me say a few words about why we care about intrinsic geometry. So before we saw x and y sitting inside some ambient affine space. But really, they are objects in their own right. You should be able to study them without reference to what they sit inside. And this point of view is actually quite late in the history of mathematics. So the reason why it's important to do that, firstly, it's the natural thing to do. If you just want to study x, it shouldn't matter about where you sit this geometric object. The ambient space shouldn't matter. And often, when you're given a geometric object, it's not naturally sitting inside anything at all. And the classic example is, for example, if you want to study the universe, by definition, the universe contains everything. So it doesn't sit inside something else. So we're going to look at intrinsic geometry, and to a certain extent, the coordinate ring allows us to be precise about what that means. Okay. So firstly, a morphism of varieties from x to y. We saw that the homomorphism that's induced on the coordinate rings captures all the information you need. So we'll just define that to give us a morphism of varieties. In other words, we'll define a morphism of varieties to be an F-linear ring homomorphism by upper star from the coordinate ring of the y to the coordinate ring of the x. So we're putting back functions. Of course, what's the corresponding map on points? Well, you can either work as in this example, and just see what it is quite easily, But you can be a little bit more sophisticated too. So let me show you how that works, because it's rather nice. And the way we'll do that is that we're going to talk about points on here using the algebraic incarnation as F-linear ring homomorphisms from the coordinate ring to F. So we've got some F-linear ring homomorphism from here to here, that's some alpha, and that represents a point X. And what I need to do is to give you a point of Y, which is an F-linear ring homomorphism from here to here. And there's a natural way to do that, because you've got an F-linear ring homomorphism from here to here, and if you compose it with this one from here to here, so you compose the phi star with this alpha here, you will get an F-linear ring homomorphism from here to here, and that gives you your map on points. And if you just go through all the calculations, it's a little bit tedious, but it's not difficult. You'll see that it recovers precisely the type of thing that we see over on this side. So that's rather nice. Okay, so let's go through a little example now and think more about this so that I can tell you more about what it means, extrinsic geometry as opposed to extrinsic geometry. So let's start with an affine F algebra R. So remember what that is. It's just something that's isomorphic to a reduced quotient of the polynomial ring in some number of variables. Okay, so in other words, you can find a surjective F-linear ring homomorphism, let's call it phi star, from this polynomial ring to R. Well, once you have this, you can see what is R isomorphic to. R is isomorphic to, by the first isomorphism theorem, this polynomial ring modulo the kernel of this phi star. So since this has the form polynomial ring modulo some ideal, this ideal here, it is indeed the coordinate ring of some variety inside AM. And that variety is the variety of kernel of phi star. So the point I want to make from this example here is that we now have a way of looking at an intrinsic description of some variety V. And that's by its coordinate ring R. And if we think of it intrinsically, we're only interested in the isomorphism class of this F algebra R. So what does an extrinsic definition mean? It means, well, you want to know how this V is embedded inside some ambient affine space. So let's look at our example here. So remember here we have some affine F algebra, and we know we can write it as the surjective image of some F-linear ring homomorphism phi star. And what does this correspond to? It corresponds to a map back the other way. A map from the corresponding variety to, well, this is the coordinate ring of A to the n. So that's how this variety sits inside A to the n. But of course, you can write this ring R as the quotient of a polynomial ring in lots and lots of different ways. There's lots and lots of choices for this, and the different choices will give you different embeddings of this variety inside A to the n. So the point here is that if you think of this variety just in terms of its coordinate ring, and you look at it just in terms of the isomorphism class of that F algebra, you're thinking of it intrinsically. But if you pick the algebra generators, which in this case correspond to phi upper star of x1, phi upper star of x2 down to phi upper star of xm, if you choose those generators, then you've chosen the way it embeds inside some affine space. And the simple example is the one that we looked at before, actually. So you might remember that we had this curve C, was this parabola here, and its coordinate ring was given by this here. And it's quite easy to see that the map that we had to f of z is actually an isomorphism. This actually follows from the first isomorphism theorem. So here we have two isomorphic F algebras, and it's certainly reduced. This one is the coordinate ring of affine lines. This is the coordinate ring of C. If you want to think of it intrinsically, they're the same. They're the same object. But this is, when you write it like this, you're thinking of it as this parabola inside the plane. So it comes with that embedding. And that corresponds to the fact that you've chosen these generators x and y. So back on this side, remember the x here will map to z plus 1, and the y will map to z squared. So you've picked, instead of the usual generator z for it, you picked the generators z plus 1 and z squared. They're still generated. And this different choice of generators gives you a different extrinsic description of this affine line. Okay, so let me just sum up one of the main points of this video here, and that's the concept of duality. And that kind of answers in what sense Sophie Germain's remark is true. How is it that the study of algebra and the study of geometry are essentially equivalent? Well, the point is the following. We have a correspondence essentially between varieties and affine F-algebras. And what's more, not only do you have this correspondence, but if you want to look at morphisms of varieties, they correspond precisely to F-linear ring homomorphisms. There is a little bit of a twist, and the only twist here is that if you have a map from x to y, then the corresponding map on the coordinate rings goes the other way, from f of y to f of x. And that's why we call this duality. I hope you enjoyed this adventure in pure mathematics.